Hello students, this is Professor Lee. Today we're going to perform the lab for forces acting on a bicycle when the bicycle is in equilibrium. For this, first we're going to quickly review the important concepts for this lab, and then we're going to do the lab activities to measure the forces acting on the bicycle using the force plate. As you just discussed, to make a body in equilibrium, all the forces acting on the body must be balanced. Also, we learned Newton's first law of motion exactly explains force equilibrium. And therefore, applying this law, we can identify what is going on with the forces in the body to see whether they are balanced or unbalanced. All right, so I bring this example we covered in the class as it will be good to review the concept needed for this lab. So what is our scenario in this example? There is a bicycle and an additional weight P added on the seat of the bicycle. As we see in this figure, the bicycle is supported by the smooth surface contact. And we see these two bicycle wheels have a direct contact to the surface. Lastly, the bicycle is in equilibrium. This is one of our today's lab projects as well. In our scenario, let's assume we know the bicycle weight acting on the point C, which is the centroid of the bicycle. In this lab, we're going to measure the reaction forces from the surface to the bicycle body using the force plate, and therefore, let's assume the reactions forces are also known. From all this information, we want to identify the mass of P added on the seat of the bicycle. All right, how to find? First of all, we need to define our coordinates to clarify the direction of the forces. So let's follow the steps we had in the class. As we learned, forces are vectors, so not only the magnitude, but also the direction of the forces are critical. So very first step, we're going to clarify, we're going to clearly define which directions are going to be positive and negative in our solutions. So here, as we see, horizontal right direction, vertical upward directions will be positive in x and y in our solutions. Then we can move to the next step. So we need to draw a free body diagram next. So as we practiced, always we start our free body diagram with FBD underbar to clearly show this is our free body diagram in this solution. All right, students, what was a free body diagram? Free body diagram is a diagram which show all the forces, which includes active and reactive forces acting on the body. How? We isolate our body. In other words, we make our body free from the surroundings. All right, if then we choose first our body, which we analyze, and therefore in this problem, this bicycle outline will be our body. And we only draw an outlined body in this free body diagram. Then don't forget, include the important geometry information such as points to be clear with the location of the forces acting in our program, in our diagram. So therefore, points A, B, C must be included in this diagram. Then we isolate the body from the surroundings. In this example, the surface will be the surroundings, and then we will isolate this bicycle from the surroundings and then show all the forces acting on the body. Let's start to show the active forces first. Due to the mass of a bicycle, the weight will act at this centroid of a bicycle, which is point C, which direction? Vertical downward direction, because the weight is acting in the gravity direction. Let's move to the P. Also, the added weight has its own mass, and therefore the weight of P will act in the vertical direction and downward. active forces are done. Pink colors are done. Then let's move to the reactive forces with the green color, as we did in the class. All right. So reactive forces from the smooth surface contact. And then as we're dealing with the smooth surface, our problem is free from frictions. But still, we will have normal forces from the surface contact on each bicycle wheel, which has a direct contact. We know the normal reaction force from the surface contact will act at normal to the surface towards the centroid of the body. Therefore, the directions at A and B will be vertical upward at this point. This will be our free body diagram. Then the last step, we're ready to apply equations of equilibrium. Our system, again, is in two-dimensional space, and therefore two equations in x and y directions can be applied. Fx equals 0, Fy equals 0. There are Fx equals 0, but there are no x-force components in our free body diagram, therefore this is not applicable. However, we have several forces in y directions, and let's apply Fy equals 0. All right, let's come back to this free body diagram to deal with all the y components here. So let's start from the pink active force, and then we're going to move to green for the reactive forces. All right, let's start from the weight. Weight downward, therefore it must be minus, as it is opposite to our coordinate definition. And let's move to P. P again downward, therefore minus P. Let's move to the green color reactive force starting from A. Then let's move to B. And we see that both are what? Upward direction. Therefore, positive R of A, positive R of B, because they do have the same direction as we defined as positive in Y. And then the summation of all the forces here must be 0. And therefore, this unknown P can be found by W minus R of A and R of B. All are unknown, one unknown P, one equation. We can find this P. But please note that we're finding the mass of P, not weight of P. Therefore, we will need to divide this P by the gravity for the mass of P value. And this will be our answer. And this will be your data analysis process after your measurement in this lab.